This is example 12-8, flow in a pipe. So in this case, it's a partially filled pipe. So it's different than if it's a full pipe. We see that water flows in this 1 meter diameter culvert and has a flow depth of 0.25 meters, a quarter of a meter. The culvert has an unfinished concrete surface and a slope of 0.02. We want to get the flow rate. And we're given what the surface roughness coefficient is. All right, so what do we do? Well, we know we have a formula that will give us our area and our wetted perimeter, but it depends on kind of this angle, right? So we'll have to figure out what that looks like. So if we draw our cross section, somewhat of a circle here, like this. Let's choose a different color. Right, we know that we have our depth here, right? We know that this distance, we'll call that distance, we'll call it y. Let's do an arrow here. Right, this would be our depth y. And we know that we have a center somewhere. So we know that this whole distance here is, of course, the radius, right? We know that this is also the radius. All right, so if this is the radius and this lower part is y, then we know that, we're going to draw this somewhere else here, have some space, right? So we know that this here, that little piece right there, right? That piece in green, light green doesn't show up all that well. Right, we know that this place would just be r minus y. And the angle that we're interested in is the little angle in here. Right, and we'll call that angle theta. All right, so how do we get that angle? Well, we'll have a nice triangle here, right? We don't know what this part of the triangle is, but we know the hypotenuse is, and we know what the adjacent leg is, right? So we can say the cosine of theta is going to be r minus y, which is that little piece that I colored in green, divided by the hypotenuse, which is r. Okay, so we're trying to find the angle, so let's say that means that theta is, of course, cosine minus 1 over that term, r minus y divided by r, which is, if we put in numbers, cosine minus 1 of 0.5 meters minus 0.25 meters divided by 0.5 meters, and that is equal to cosine minus 1 of 0.5. And now, very importantly, we're doing all this in radians, right? Not in degrees. But if we know the cosine, right, then we know that this is pi over 3. Now, we're not interested in that half angle. We're interested in the full angle. So my alpha that is going into all my equations is going to be 2 times theta. So that would be 2 pi over 3. Right? That's our opening angle that goes into our 2 equations that we have. One for the flow area and the other one for the wetted perimeter. So we start with the area. Then we can say A is equal to r squared over 2 times alpha times, not times, but minus sine alpha. This is why we have to have our angle in radians, right? For the sine, it doesn't matter, but up here, it has to be in radians. All right, so let's plug it in. So that'd be 0.5 meters for our radius squared, right? Had a 1 meter diameter, divided by 2, and then times 2 pi over 3 minus sine of 2 pi over 3, and that is equal to 0.1534546 meter squared. So that's our flow area. Now we also need to have our wetted perimeter. So that equation is even easier. P is equal to alpha times R. So for us, 2 pi over 3 times 0.5 meters. So that is 1.047198 meters. All right, with that we can get our Q. Q is equal to a to the 5/3 times the slope, or the square root of the slope, divided by n, which is the only one without an exponent, and then p to the 2/3. All right. So that is 0.153546 meters squared to the 5/3 times the slope was 0.002 times 0.002 to the 1/2, square root. N is given to us as 14, so 0.014, and then again our strange unit, S over meters to the 1/3, times, and then our wetted perimeter, 1.047198 meters to 2/3. All right. So that is then 0.136385 cubic meters per second. Let's see if that makes sense. Where our seconds are right here, so that's good. Now our meters. What do we get? We get up here, we get 10/3. Let's do down here for 10/3 plus 1/3 will be 11/3. Let's do a little 11 up here. So it'll be 11/3. And then down here, we have 2/3. 2/3. So 11 minus 2 is 9. 9/3 is 3, so cubic meters. Excellent. So our units fit well. Round this 0.136 cubic meters per second. And that was what we're being asked for. All right, so we found what the flow rate is in this partially filled concrete pipe.